Okay, yeah, I'd like to speak about some high performance and scaling techniques that we've been doing in Golang. Small breakdown of the presentation, a few slides about myself and some work that we do with Minio. You understand me or not? Okay. Is this better? Or?
Nee, je kraag zit ervoor.
Oké. Waar kan die beter zitten dan? Is it better like this? Okay, great. A little intro about myself and Minio. Then I'd like to speak sort of in general a little bit about the Golang or Plan 9 assembly capabilities that Go offers. Then discuss two sort of projects that we've done with this. So Blake 2B acceleration and SHA-256 acceleration. And finally some slides about some distributed syncing stuff that we've been doing. One slide about myself. I've been mostly doing software development in sort of what's called the medical imaging space. So that relates to like CT and MR images from scanners, both 2D, 3D, as well as using GPU techniques. And the last few years, been involved in cloud computing, and I'm now with Minio. Minio, as maybe some of you know, is an Amazon S3 compatible object storage server. It is written in Golang under the Apache 2.0 license. The company was actually founded by Anand Babu Perishyami, who maybe some of you know as one of the guys behind the Gluster FS system, which is in itself a distributed file system, which is now part of Red Hat, actually. If you look at Minio itself, there's actually sort of really, one project, one binary, but you can run it in sort of three different flavors. So the simplest version is simply run Minio server with a single directory, and then all your objects will be stored underneath this directory structure. And there are also two other versions that use a technique that is called erasure coding. So what this essentially does is all the objects are split up into both like data chunks and parity chunks, and split over multiple disks or multiple servers. And the Minio server actually, the Excel backend, which splits the data over multiple disks, goes from a minimum of 4 disks up to a maximum of 16 disks. And it also uses a technique that is called bit rot protection. So this means that when the data is being read off the disk again, which can be many years later than when it is stored, a hash is computed to detect any bit rot changes. And if that happens, then we have other parity blocks to reconstruct the original data. But as you can imagine, this bit rot protection is a very frequent operation. So any data that's written to disk, hashes have to be computed. And likewise, when data is being read off the disk, the hash needs to be computed as well before we actually can return any information to the client. So that's a pretty operation for us, and that's why we really looked at how can we get sort of the maximum performance in terms of hashing speeds while still, having a solid proof and hashing technique. So that's actually how we did our Blake 2B project. But before I go into that, let me explain to you a little bit about sort of the Golang or Plan 9 assembly capabilities. This is actually an integrated or integral part of the whole Go tool chain. And it's actually, it's kind of like a pseudo assembly language in the sense that it's not the direct assembly that you would write for, say, an Intel platform or an ARM platform. So there are some like generalized instructions for like a move and an add and a compare. And these instructions are then obviously translated to the actual instructions that will run on the underlying hardware platform. Most of the time, it's kind of logical how like this pseudo-assembly language translates into the underlying assembly running on the CPU itself. Sometimes, yeah, that is not the case. It's sometimes a little bit of trial and error there. And also some architectural aspects of the underlying architecture, they shine through. So on the ARM, you have like conditional instructions, and you can do that too. And obviously on an Intel, that will not work. Also, for instance, data flows from left to right. So if you do like a move, you have a move R1 to R2. It's actually R2 becomes R1. And yeah, like on the ARM platform, it's the other way around. So there's some things you have to be aware of. There's also some, like pseudo registers. So they're not actual registers, but kind of like simulated registers for like frame pointer, stack pointer, program counter. And also, not all instructions that you would want to write are available. However, it is possible to also, not use sort of the mnemonics, but use the actual opcodes that will go into the assembly. So if it's not available, you can resort, to that. If you talk about what are sort of the advantages that you get with like assembly language, and obviously it sort of gives you the ability to get the maximum performance out of the underlying hardware. And also, if you do this, then you still benefit from the nice, quick, and fast compilation that Go offers. To get like assembly into your code, you can also use, for instance, the CGO route. But that has some disadvantages. One is that you need to have the CGO available. It takes longer to compile because again it's more like a C-style compile that happens. And also when you call into that code, then there is some runtime overhead because all the stack needs to be saved and everything. And if you write your own assembly, you don't have that overhead. And obviously, if you use assembly, you can take advantage of the SOMID instructions for Intel or the Neon instructions that are available on ARM. As maybe a little bit kind of a word of caution is that you are a bit on your own if you do this kind of stuff. The documentation is kind of limited and a little bit sparse. There is a considerable amount of kind of example code in the Go repository itself as well, for stuff like mutexes and some lower level stuff. So actually, if you grab for star.s in the Go code, you will see a lot of examples there. And likewise, we now have a few repositories where there's also some Go code in there. And as an example, basically, this is actually also a file where you can sort of see the translation between this pseudo assembly language and the actual ARM instructions as they are being generated. If you want to integrate assembly into Golang, then you have to use the .s extension for basically assembly. And that is actually prepended by sort of an architecture identifier. So _ARM64 means that the assembly is for the ARM 64-bit platform, and likewise AMD 64 will be for the Intel or AMD 64-bit platform. And actually here is a snapshot of a repository. It's a little bit hard to read, but here actually you can see actually several versions for the AMD 64 platform, because in this repository we actually have a dedicated AVX2, AVX, and an SSE version, and then there is an ARM version. I'll talk a little bit more about sort of AVX2 and AVX later on in the presentation. So kind of one approach that has worked nicely for us is if you do this kind of stuff, is to actually start out with an algorithm at the Go level itself. Because well, even if you do this, then you are not likely to do all the work for all the different architectures that are out there. So it always makes sense to have as a baseline sort of the functionality in Go itself. And then sort of as you start to translate that functionality into assembly, what we sort of did is we started out kind of like with small bits and pieces. And so you comment out most of the Go code in your routine or class or whatever. And then you start to translate small bits and pieces into assembly, maybe initially starting just with passing in the arguments and writing back some results, making sure that all works. And once you got it working, then you gradually start to translate more and more of your Go functionality into assembly, and along the way, make tests whether the assembly functionality is equivalent to the Go assembly. So actually, if you look, for instance, at the commit history of the Blake2B SMID repository, you can actually see how we used this technique. Along the way, we also developed a small utility called SM2 Plan 9S, which actually generates byte sequence codes for opcode or assembly instructions that are not natively supported by Go itself. So actually, it uses the YASM assembler sort of behind the scenes. So what you do is you basically write your instruction as you would write it regularly in assembler or in assembly, and then you run the tool on the file, and then it will prepend that instruction with the actual opcodes that will go into the byte stream that will be executed. So that has worked nicely for us. If you look at what we have done with assembly, we've actually accelerated the Blake2B algorithm as well as the SHA-256 algorithm, and we're planning to do one more piece of work, which has to do with this erasure coding, which is actually called Reed-Solomon. And this uses some what they call Galois field arithmetic, polynomial multiplications, and ARM actually has a specific PMOL instruction. So we want to use that instruction to accelerate the Reed-Solomon computation of the parity blocks for ARM. For Intel, it is already accelerated, but we want to do the same for the ARM platform. And maybe when there is a need in certain pieces of the code, then we will likely do more. Okay, so the first technique that we accelerated is a hashing technique that is called Blake2B. Blake2B is a hashing technique. It was actually there was like a SHA-3 competition a few years ago, and they were one of the 5, I think, final contenders. In the end, they were not selected, but it is a nice hashing technique with sort of the characteristics that it's really focused on speed, as well as kind of like a relatively simple algorithm to implement, while at the same time still offering sort of top of the bill security. And it's really optimized for 64-bit platforms. So we developed a repository using the SMID instructions to accelerate the Blake2B algorithm. And actually, we did it in sort of 3 flavors. So there's an AVX2 implementation, which is the fastest. Then there's an AVX, and then there's an SSE implementation. So depending on what your CPU support, then obviously the highest level of SMID instructions that is supported, that one will be used. But overall, we were able to achieve close to like a 4x performance improvement over the Go, the high-level Go functionality. So that helped us quite a bit, because if you look at the table on the right, you can, it's a little bit too small, but we can do about 850 megabytes per second with the Blake2B algorithm on an AVX2 machine. And this compares to, if you look at SHA-256, that is at like 190 megabytes per second, and SHA-512 is at about 300 megabytes per second. And as an object storage, you can imagine if you have large blobs of data written on the disk, then, and again, for us to be able to return like the first byte when people ask for an object, say if it's a 1 gigabyte object, then having a factor of 4 there, that means the difference between being able to return something within a second or within it taking 4 seconds. So that's a pretty significant saving there. And again, yeah, so we developed this technique for the bit rot detection mechanism that is part of Minio. If you look a little bit closer at sort of how it works, the top line, there's a very small portion of all the kind of computations that are happening as part of the Blake2B hashing. So there's basically 4 additions there, and these are on 64-bit integers. If you look at the AVX capabilities for the Intel platform, you can essentially work with 128-bit wide registers. So this allows you to do literally like 2 additions in parallel. And this is kind of what you see here. So with AVX2, you use what are called the XMM registers. So again, those are 128 bits wide registers. So essentially this means that whereas here, it's kind of like 2 lines, you can do it here basically, in a single line. And likewise, the second XMM instruction will also take care of 2 of these guys. So you can sort of go from like 4 instructions to like 2 instructions. And if you go one step further, AVX2 extended the pipeline to 256 bits wide, which means that you can use or do essentially 4 64-bit additions with a single instruction. So that's actually this guy, and then here you use the YMM registers instead of the XMM registers, and again, those are 256-bit instructions wide. So in a way, this kind of explains why there's kind of a 4 times speed up between, like Golang and AVX2. There's a bit more there, but I mean, fundamentally, this explains it quite a bit. If you look at Blake2B, the algorithm itself, it actually has sort of 12 rounds of working on the data. This is kind of like the preamble where first the message is being read in, then it's kind of shuffled around, and then there are 2 sort of macros that actually do the actual like XORing and adding and rotations of all the bits. Then there's like a diagonalize macro there, which kind of rotates values between the different values that you are working on. And then there is a second half where you load more from the message, you shuffle it again, and you call the same macros again, and finally you undiagonalize, so you sort of shift it back. And if you look at one of the macros, so in this case this is the what's called the G1 macro. It actually consists a little bit of like 3 columns. So on the right side of the screen you kind of see the high-level Golang instruction. Then in the middle part of the screen you sort of see the AVX instruction, and then on the left side of the screen is the actual opcodes that are being written into the assembly stream. And so actually what this guy does is here there's like this is an addition, this is like an XOR. Here you actually see a rotation, but the Blake2 algorithm has selected like shift values that nicely map onto the Intel architecture, so you can actually while it's a shift over there, it's actually a shuffle. So you shuffle bytes around in between the registers. So, and then there's more additions, more XORing, and then yet another kind of rotation. And this happens, over and over again, and then in a total of 12 rounds, and that's, how you get your hash out there. Okay, that was about the Blake 2B algorithm. We've also done some work on the SHA-256 algorithm. Most notably also for the ARM platform, because the ARM platform actually has specific instructions to accelerate SHA-256 calculations, and they make a tremendous amount of difference, because it literally is 100 times faster than not using those instructions. And actually Intel also has instructions for SHA-256 accelerations, but they seem to be just defined in software, and there seem to be no hardware implementations out there. Otherwise, it would be nice to take advantage of that as well. But actually, the table here at the bottom, you can sort of see the speeds that we have. And interestingly speaking, actually, the ARM just running at 1.2 gigahertz is actually the quickest one out there. So it does about 640 megabytes per second, and then we ran some tests on an Intel Xeon at 2.4 gigahertz. The AVX2 comes in at about 355. Then the AVX is running around 300. SSE still a little bit lower than that. And these are actually the Go versions. So if you do Go on the Intel Xeon platform, you get about 190. And the last one is the ARM version. If you look at how do you actually invoke assembly code from Go, you essentially define kind of the prototype of the function that you're going to call into. So for most of these hashing techniques, you pass in like the digest that you start with, and the message itself. So the digest is basically just a slice of 32-bit integers, and the message is just a slice of bytes. And here we actually compute the 8 32-bit integers into the digest. So that's this guy, and then basically the actual message that you're going to hash is being passed in directly into what will be the assembly code. And then once you're done, then actually the result is written in this guy. So that is what you return. This is actually an ARM example. So the first line, that's basically how you define the function in the assembly code. And the first thing that you actually do is to read the parameters that were being passed in. And this function takes 2 slices as inputs. And as maybe some of you know, a slice is actually a structure with like 3 elements in it. And the first element is a pointer to where the actual data is, and the second is actually the length of the slice. So what we're doing is the first few instructions were reading this here, and because this is running on 64-bit platform, both slices in effect they take up a total of 24 bytes. So again, it's 3 elements, but each element is 8 bytes long. So the first instruction basically fetches a pointer to where the digest is. And the second line fetches a pointer to where the message is, and then the length of the message is being read at in the third statement. So it's another 8 bytes further than the already 24 bytes, which point into the second slice that is being passed in. And then further down here, we do some initialization. So here we load from x0, which corresponds to R0, the digest. We also load, obviously, from the message itself, and there's also a constants table. So we get basically a reference to the constants table that's actually in R3, and R3 corresponds in Neon to X3. So here we load values from the constants table, and this is actually sort of the main loop where the hashing is being done. And again here, R1, which is X1, is the pointer to the message. So here actually the values from the message are being read. And well, there's some like positioning codes to make sure things are in kind of the right order. And then these guys are actually the specialized ARM instructions that give basically the 100 times speed up. And then there's some more shuffling of data around, but because these are specialized instructions, the actual assembly is pretty short. And then this is like the end of the routine. So again, there's some ARM instructions or SHA extensions instructions here, and then here it's basically put into V1 and V0 and V1, and here actually you write out the result in like register 41 and V1 into X0, which was the pointer to the digest, and then you return out of there. And obviously here, well, as long R2 is the length of the message, so you process 64 bytes at a time, and just when there's more work to do, obviously you loop back. And, so that's pretty much how a function like this looks a little bit. If you look at some resources that we have that are out there, actually, as maybe some of you know, some of the origins of the Go, like architecture and work go back to the whole Plan 9. Work on that has been done, and actually, some of the assembly, still originates back to that. So some of the documentation out there, is literally at the gp.io website. So not everything in those URLs is kind of applicable. Most of it is, but they're generally good resources to read through and get an understanding of how this all works and ties in together. And then there's also like a high-level SM document, and there's also some pointers for ARM, some pointers for Intel about how Neon instructions and AVX instructions work. Okay. That was sort of the the performance optimizations that we've done for hashing techniques. We also did some work on something that we called a distributed syncing technique. When I earlier talked about the 3 flavors of Minio that are there, the last one that was listed is called the distributed version. And so we have 2 versions that can work with erasure coding, and then distributing the data across multiple either disks for the XL version or actually multiple servers for the distributed version. And for the distributed version, that can actually run from anywhere of a minimum of 4 servers up until a maximum of 16 servers. We needed to have a synchronization mechanism between the servers. And we also looked at some existing protocols and techniques out there. But we like in a technique like Raft. But we found that a little bit overkill for sort of what we were trying to do. So we designed basically a pretty kind of minimalistic synchronization technique that works well for us. The design goals that we wanted to have was basically keep the design simple. Also meaning there's, for instance, no concept of like a master node. Because, well, if you have something with a master node and the master nodes goes down, then yeah, your whole system is down. So you need to have backup master nodes, and then you already talk about 2 or 3 master nodes, and it quickly starts to become, more complicated than what you initially think. So in our system, there's no concept of a master node, so all the nodes are basically equal. It's also resilient in the sense that if multiple servers go down, the system just continues to function. So basically, up to a total of n/2 minus 1 servers can be down. You can continue to function. We also wanted it to be kind of like a drop-in replacement for the existing primitives that are there in the Go language. So the API or the interface is synonymous to the sync.rw mutex and actually the sync.locker interface. As part of our requirements, we maximized sort of the maximum number of nodes to a total of 16. You could actually, if you wanted to, push that number up a little bit, but 16 is good enough for us. And how this works behind the scene is that all servers basically have a connection to all of the other servers, and when one of the nodes asks for a lock, it basically contacts all the other nodes. And when a majority of the nodes return back the lock, then the lock is granted on that particular machine. And when you release it, again, it sends out release messages. And so it's relatively simple, but for us it works quite well. Here as an example, maybe a little bit difficult to read, but again, the API is compatible with the regular RW mutex. So basically, this is an example where you just create a mutex, and then you lock it twice. And then there's some Go routines that after 1 and 2 seconds unlock the read lock. And then here you try to acquire a write lock, and obviously the write lock can only be granted when both of the read locks that were earlier granted were released. So you can sort of see here that, so it's acquiring read lock 1, read lock 2, and then it's trying to acquire the write lock, but it will block here until both the first read lock and the second read lock are released, and only then will it require the write lock. And obviously running this on a single machine is not really the point, but you can just as well create basically 3 of these named mutex on 3 machines, and then run one read lock on one machine, another read lock on another machine, and the write on the third machine, and then the whole sequence of events would be identical. In terms of like performance, on a 16-node configuration, we were able to do like 7,500 locks per second. And then it takes about sort of 10% CPU usage on like a a regular server. And typically a lock is granted within like 1 millisecond. So this quite nicely met basically our requirement in terms of an object storage. An object storage does not have the requirement that you're going to write like 100,000 objects to it in like a second. So maybe for something like a key value store, this wouldn't work. But in our case, it quite nicely met our requirements, and so it's nicely bundled with the menu distribution. And actually, here's a pointer to the repository, and we also on our blog we have a blog post about this with some more details. So that pretty much brings me to the end of my presentation. Thank you for your attention. And, go ahead.
So I have a question. So you are using Blake to detect bit rot,
Correct.
and then you have performance problems, but Blake is a secure hash. So why don't you use an error detecting code, which is probably much, much cheaper, instead of using a secure hash and then, you know?
What do you mean by an error detecting code?
Well, actually something like Reed Solomon or probably Hamming or, I don't know, something which is cheaper.
Reed Solomon doesn't give you bit rot. I mean, Reed Solomon
well, it detects
gives you
bit flips. So
no, not by itself.
well, maybe Reed Solomon. I can't remember. I have to look it up. But Hamming codes, for example, detect errors, and there are much better suited codes for detecting bit flips.
No, the problem is there's parity blocks computed in Reed Solomon. But imagine you have two data blocks and two parity blocks, and when you lose, say, 2 disks, so you're down to 2 blocks, then if you just have 2 blocks, you have no way to determine anymore whether there's bit rot or not. So you're right, if you still have all the data and parity blocks available, you could work out whether a block that you read off the disk has not been unchanged, but it would be not easy to do so. And when you lose those disks, so you're down to the absolute minimum that you need in order to be able to reconstruct, then you have no way to detect bit rot anymore. Right?
We talk about this later. I don't agree yet, but let's.
Hi. You mentioned that this code doesn't rely on Seago. Is there any complication at all compiling this kind of programs?
No, it does not rely on Seago, but what is your question?
Well, is there any complication compiling this program, or is it just a Go build and that's all?
That's it. If you do a Go get, you will get all the repositories, and it just builds normally. And there's you just need to have the Go chain installed, but no special other options or features of the Go toolchain.
Okay, it will just adapt to the platform, to the CPU, and this kind of thing.
Yeah, no, absolutely, yeah.
Right.
Mm-hmm. Any other questions? No.
Oh, there's
Thank
a
you.
question there.
Oh, coming.
I was just wondering, how did you write the assembly? I mean, you showed us all these opcodes. Did you use some other assembler and then extract this, or how did you?
For that, we developed basically this tool. So we developed this SM2 Plan 9S tool, which is also here you see the repository. So basically, this is what you write in your assembly file, and then you run SM2 Plan 9S on this file, and it will prepend like the byte sequence.
Oh, okay. Sorry, right? I missed that. Okay, thank you.
Yeah, otherwise it's a bit cumbersome. Pretty cumbersome.
Any other questions? No? Oh, yes.
Okay. Oh.
Could you pass that mic?
Yes, my question was regarding to your SHA-256 implementation. Have you thought about contributing it into the standard library?
Yeah, we were planning to do that, but we need to do a bit more work for that. But that will be coming, yeah.
Because second question, how come your implementation is faster than the Go standard library for AMD 64, since both are in assembly and have an AVX2 implementation? So what, did you do something special?
Well, I mean, there's different ways to do different things in assembly, right? So, I mean, it's not going to be a factor 2x, but I mean, depending on how you exactly do it, you may see like still minor, differences. So, just like in regular high-level Go, you can also one maybe way of doing things maybe slightly better than another way of doing it. So,
thank you.
okay, thank you.